Okay, so where we left off yesterday, we were talking about how to find areas under curves, right? And there is a need for that. It may seem like a fairly bizarre thing to want to do, to find areas under curves, but it's a really big deal, and there's lots of significant applications, economics, science. There's lots of areas where you want to find, or lots of studies where it's important to find areas under curves, cumulative areas, what you think about it as being. Okay, so let's talk about how we could do this. Well, here's where we kind of left off yesterday. One way we could do this is if we were going to embrace the idea of just of finding an area by using better and better and better approximations of that area until you get a good enough answer, right? And we used what's literally called the method of exhaustion, probably appropriate for this time of year. But the method of exhaustion would be, if we want to find the area of a circle, we're going to find n-gons of larger numbers of sides that circumscribe and inscribe the shape. And then by gradually kind of increasing the numbers of sides, we're going to clamp those down on the circle and exhaust all the extra area. We're going to push it all out there so there's very little extra area, we're not going to overcount or undercount the area by very much. And eventually, if we keep doing that, we let the number of sides on the polygon go to infinity, we'll completely exhaust all that extra area, and we'll arrive from larger areas and calculating areas that are a little bit too small will converge on the same limit, which will be the exact answer. So you get the idea, right? Well, we want to apply that same kind of thinking to an area under a curve, right? And the way we can do this, and it seems like a little bit odd, but you'll see the merits of this as we go through it. We're going to do this by defining circumscribing and inscribing rectangles. And we're going to, if we let, those are going to approximate the area, right? And so if we're going to take an example, like let's say we're going to look under the curve. Here we've got the function f of x equals x squared, and we're just going to look on the interval from 1 to 4, right? So we're trying to find that area right there, right? Area under f of x equals x squared on the interval from 1 to 4, okay? So we can do this by defining these rectangles, but in order to define rectangles are really it's easy for us to find areas of rectangles. That's why we choose that shape. What's the formula for the area of a rectangle? Well, meaning more broadly, length times width, or width times, in this case, we'll think of it as being width times height, right? Well, the first thing we have to do is we have to define what the width of the rectangles is going to be. Now, there are some arcane cases, and we could go into great detail about how to use this very specific type of calculus involving limits to find areas under curves. And if you got really good at it, there are some cases where we wouldn't necessarily want the rectangles to have uniform widths. But we're not going to do that because we're going to end up with a shortcut that's a far better way of doing this anyway. So in order to get to that point, we're going to pick pretty generic cases just so we can see how this all works. So for all the examples we're going to pick, which are going to be just polynomials, right? Easy functions. And then we can generalize this to other functions later after we know the trick. It's going to make things far easier if we just let the rectangles all have the same width. Okay? So let's say, for example, we're going to define the number of rectangles. We're just going to call that n, unsurprisingly, the number of subintervals and the number of rectangles that we're going to use to approximate our area. If we're going to just arbitrarily say, let's let n equal 12, okay? And our area that we're looking for spans x equals 1 to x equals 4, how are we going to find the width of each rectangle? Yeah, just divide the whole width of the area by 12 to get the width of each of the small subintervals, right? The interval from 1 to 4 is an interval of length 3 divided by 12, and that's what we do, wouldn't we? We'd say delta x, what is x? Delta x equals 4 minus 1, there's the width of our interval, divided by 12, which is just going to be 3 over 12, which is 1/4, right? Or if we want to write it as a decimal, 0.25, okay? So that's gonna be the width of each rectangle, and so we can see that. We're gonna start off with the left edge of our areas at 1. The first subinterval is gonna span the width from 1 to 1.25, and then from 1.25 to 1.5, etc., all the way until we get up to 4. We're gonna carve out 12 subintervals, right? So for each subinterval, and we can label these, we want to do this. First one is going to be subinterval 1, the second one is subinterval 2, the third one is subinterval 3. If we want to kind of keep a running tally of this, and this will sort of harken back to the discrete math you guys did last year with the sigma notation, we could just say we've got some random one in the middle here that we're not going to really pin down, that we're going to call the ith subinterval. And we're just going to let I vary from 1 up until 12. Doesn't that kind of sound like sigma notation stuff?
Yeah, we
right?
didn't talk about sigma notation at all.
You guys didn't do any sigma notation?
No. It doesn't look too hard though. You just put the number that you want to go to for whatever you want to do, and then you put them. Yeah.
Okay.
Not that bad.
Okay, well, okay, let's take just a second and talk about sigma notation. And then and I'll talk more about, I want to talk about it, man, if we had that month back from the snow days, I'd take a week here and talk about sigma notation. But I feel like I don't feel like that's the right thing to do. Okay, but we'll do just a tiny bit. So sigma notation. This means sum, right? These are called discrete math. Which means we're talking about math of functions that come in discrete pieces instead of continuous, right? So for example, you would count, I know this is like grade school stuff, but I want you to make this connection. If we're counting the number of, baseballs in a bin, that is a discrete function because you can't have half a baseball. They come in increments, right? Same thing with discrete math. So you're talking about incremental math. It comes in discrete increments as opposed to a continuous function, like the weight of sand in a truck as you pour sand into the truck. That's going to continuously vary. If we assume the sand is infinitely small, we're not going to nitpick. So then, for discrete math, we want to be able to sum things up, right? We want to be able to add up the discrete numbers of things, and the way we do that is with a summation. And so we could do something like if we were to say the sum of I as I goes from 1 to 5, well, what is that?
1 plus 2 plus 3 plus 4 plus 5.
Okay, so that whatever the argument of the sum is, so this is like what's inside the summation function, so to speak, right? So that's why I always call that an argument. The argument of a sine function is the angle you feed it, right? The argument of a power function is whatever you're taking to a power. So the argument always has to have an I in it. Well, it doesn't always have to, but that's the thing that we're going to add up this many times. As the value of I varies from 1 to 5, we're just going to add up what each individual term is for that particular value of I, right? So this is going to end up giving us 1 plus 2 plus 3 plus 4 plus 5, because those are the values. This is the value when I equals 1. This is the value when I equals 2, etc. Right? And we just get some answer. Okay, usually for large sums, we'll just use technology to add that stuff up for us, and I'll show you how to do that. Okay? And let's take one a little bit harder one. What if we had something like the sum of
X squared.
I squared plus 2 as I goes from, let's be really tricky. Let's go. We're not going to do this today, but we could start I any place we want to. Let's go from 2 to 5. So then we're going to have the term that goes with I equals 2. What's that going to be?
Substitute 6.
I'm going to get 6. Good. I'm going to get 2 squared plus 2 plus, when I equals 3, we're going to get 3 squared plus 2, which is 11, right? Plus, etc., all the way up to 5. Okay? So you get the idea? That's what a summation does. It's a really powerful tool. If we want to do something like this on your graphing calculators, I'll show you how you do that.
Paul doesn't know.
Well, okay, but I want you to see it on your TIs too, because you're likely to use those in college a lot. Some classes, they may only allow you to use the TI-84s, for example. Like in engineering classes, I think that would be pretty typical. I don't know. Desmos is so good. You gotta know how to use that too. So if I want to do this, right, here's where you go. You go to the math menu. If you have your TI-84s, just get them out real quick and go through this. And I am recording this, so I'll leave all these videos up there. You guys can get into this, in the future if you want to. I'll leave them up there, so if you want to look at notes next year or something, you still can. So we go to the math menu, and then we go clear to the bottom, so I'm just going to go up to the top because it just loops around. So if we go up from the top, we want to stop, obviously, at 0, summation, right? So if I choose that, and now it's pretty self-explanatory. You could probably take it from here. Right. You can't use the variable that the calculator always assumes you're using x. Right. So instead of an I, we would just put an x there. Although I wonder if you can use an I.
You can do any variable.
You can. Okay. So you could do an I. It's easier just because there's an x right there. It's easier just to use x. So x would go from 2 up to 5. And we're just adding up x squared plus 2, and it adds it up. How simple. Okay? In Desmos,
Desmos is pretty self-explanatory too.
yeah, it
You
is.
go to miscellaneous stuff. You can not just type sigma. You probably could. But it's a pain to type on the app.
So if you might, I think if you just do sigma, no, it doesn't do it. So you have to go down to the keyboard and you go over to functions, miscellaneous, that's where all the calculus stuff is. And there's your sum. And they use n, but in Desmos we can change that to anything we want. So we'll go, I goes from 2 to 5, and we're just adding up I squared plus 2. It gives it to us. Okay, so very handy. Okay.
What would
Okay, so does it make sense then? And we'll get back to this. You'll see some more sigma stuff here, but you kind of get just a loose idea for now what this is all about. So does it make sense that sigma notation would really be a useful tool to us here, right? Because we want to add stuff up. To find the total area, to approximate the total area under the curve, we want to add up the contributions of each rectangle, right? So if we kind of think about this big picture, we think about this like a problem we're trying to solve, all we got to be able to do is define each of these individual areas in terms of which rectangle is it, 1 through 12. So based on which rectangle it is, if I can come up with a way to define the area in terms of, for example, 3, define this one in terms of the fact that it's the second rectangle, I can just sum them up then, 1 to 12, and I'm done, right? Okay, so how are we going to do that? So here, these represent the rectangles. Well, we know what the widths of all of them are. What are the heights going to be determined by in this case?
height of the function?
Okay, the height of the function where? As I've drawn them here, the height of the function where? So if we want to look at this first rectangle, the width we already said is just 0.25. But the height is determined by the value of the function where? Okay, but you didn't say which end.
Right.
At the right end, okay? Because we could have also done it, and that works for all of these rectangles, doesn't it? Each one of these rectangles is built so that the width is just what we called our delta x, right? The width was 0.25, but the height, in this case, is determined by the value of the function at the right edge of each subinterval. Now, if the function is increasing like this one is, can you see that that means the rectangles are going to be overestimates? They're going to be circumscribing rectangles. Everybody see that? We could also do that if we wanted to. We could also define the rectangles by their heights at the left edge, right? That works. I'm doing the same thing. The widths are still 0.25 here, but this time the heights are determined by the value of the function at the left edge of each subinterval. Because this function's increasing, that's giving me circumscribed rectangles, so I'm going to undershoot the area. Okay? You see maybe a strategy there, though. I mean, if I want to make an estimate using only 12 rectangles, and I want to be pretty accurate, what could I maybe do?
Average the summation of both.
Good. Average the two. Average the circumscribed ones, which are defined by the right edges, and the inscribed ones defined by the left edges. That's going to get me fairly close, right? Closer than in either individual approximation. Okay? Okay, so then we could do this, and you notice here, if we combine the two, you're going to see something pretty important. Obviously, the blue ones are the overshooting, the red ones are the undershooting, but you see another relationship there between what we're going to call the right sum and the left sum. The right sum is the sum using the right edges of the subintervals, and the left sum is the sum using the left edges of each subinterval for the heights.
The difference increases.
Okay, but watch this. You notice something? Oops, let me grab that.
There's a right triangle in the
See that?
Yeah.
Cool as that, right?
That's
So
right.
they're all, doesn't it make sense? Because doesn't the right edge of the first interval become the left edge of the second subinterval, right? And so if you ignore the very first rectangle and the very last rectangle, we're adding up the same sum, aren't we? Everybody see that? Like if I scoot this thing to the right, unfortunately, like if I scoot this to the right, the second left rectangle becomes the first blue rectangle, and the 12th red rectangle becomes the 11th blue rectangle. So if I wanted if I wanted to turn that into a blue sum, I could just ignore that one, just get rid of that one, but I'd have to add an additional one at the end. Okay. So you see that if we were calculating manually, we could save a lot of work here, right? We know that rectangles in the left sum, rectangles 2 through 12 become rectangles 1 through 11 in the blue sum, and all I got to do is subtract the first and add the 12th, and that gives me my right sum. I've done most of the work already. Everybody get that? Okay? So if we wanted to add these things up, how could we do that? Well, this is just a simple, if I've got a finite number of these, if I've got 12 of them, all I've got to do is just come up with a convenient way of adding all those up. Now, we could add them up one at a time. If you only have 4 or 6 of them, I mean, really, it's quicker just to figure out, okay, what's the value of the function there, what's the value there, just find the height and the width of each individual rectangle, calculate the areas and add them up, right? And that's literally what you would do on a calculus problem that asked you to do that. Well, when you start getting out to 12 or 20 or something like that, some finite number that's bigger, that sounds like a lot of work, doesn't it, right? So can we come up with a better way of doing this? We can. And what I want to show you here is, I want to illustrate that point, but I also want to introduce you to the wonders of Desmos, because you're going to probably use Desmos a lot from here on out in your math careers. So, I got about 1 billion of these I built. I got to find the right one.
Do you think there will ever be a time when Texas Instruments starts replicating programming on Desmos?
I don't know. The TI-84s work better. They're better algorithms, but they're just not as convenient. So if we do something like this, let's do the right rectangles. How about? So that's the blue one. Okay. Here's a way we can do this. I want you to just kind of try to follow along with this. This is really easy to do things like this. Desmos is super easy to define functions and use those functions within other functions. So if our function is f of x equals x squared, there's a graph of f of x equals x squared. What we want to be able to do, though, is we want to be able to find the areas of the individual rectangles 1 through 12. So what we could do then is we could let the variable I be the number of the rectangle, right? So we're going to define this other variable I. And I'm gonna define the function capital X of I is just telling me what's gonna be, this is gonna be the right edge of the ith subinterval. Okay, so we're starting off at 1, aren't we? If we look at our picture, if we go back to our picture, right? We're starting at 1 and we're going to 4. So we would say in calculus that we're going from A to B, and A is the left edge of our region, that's A, the right edge is B. So A is equal to 1. So if we want to figure out where the right edge of each subinterval is going to be, it's going to be, we're going to start at 1, and then think about them as steps. If I want to go from x equals 1 to x equals 4 in 12 steps, we already know I'm taking steps of length 0.25 each time, right? So if I want to get to the right edge of the first subinterval, I'm starting at the starting line, and I'm taking how many steps? 1, right? So I've got 1 plus 0.25 is the length of my step times I. I would be 1. If I is 2, I'm starting at 1 and I'm taking 2 steps, and that puts me at the correct x value, right? If I want to find the right edge of the 7th step, I'm starting at 1 and I'm taking 0.25 times 7 is the distance I've covered, okay? So this function right here, does everybody see this? That if I plug in a certain value of I, it's defining the edge of the interval, okay? So now I want to know what's the area of each rectangle going to be? Well, area of a rectangle, you already told me, is just width times height, right? So the area function of the ith subinterval is going to be, the width is always the same, it's 0.25. So this is literally just, this is just the width. Now what's the height going to be? Well, the height is based on the function, isn't it? You already told me that. Right? So the value of the height is determined by the value of the function at the right edge of the subinterval. Well, that's what we called x sub I, right? So it's just f of x sub I, isn't it? So in Desmos, I already defined what f of x is. So all I have to do is evaluate the function f at x sub I. It's pretty cool, right? And that's giving me, whoops, that's giving me the height, right? And so that's telling me the area of the ith rectangle, 1 through 12, okay? If I go down, and now if I want to start building, let's say, a table here that's going to show me that stuff. It's going to show me, like in Desmos you can do this. Like if I want to build a table that's going to show me what are the x values in one column and what are the areas of each individual rectangle at that point, or if I want to know the heights of the functions, I can easily build that. All you have to do to build a table like this is you go up to the plus menu and you choose a table. Okay, and this is really not a well-known feature of Desmos, but super, super useful. And then if I'm going to define I sub 1 is going to be the list variable. Okay, and I'm just going to type in I sub 1 up there. Then I've got x of I sub 1. I can do f of x sub I. I can do a function of a function. I can do f of x sub I, f of x of I sub 1. And then as I add numbers to this, watch what happens. It just populates the list. So we know that for the first rectangle, I sub 1 is 1.25, then 1.5. Well, if I just keep hitting enter, look what it does. It just keeps adding. Right? Isn't that cool? So it gives me all the x values. It tells me the value of the function there. But look, I got another column where it's telling me the areas. These are the areas of each individual rectangle. Okay? Make sense? So notice that the areas are getting, the area of each rectangle is predictably, they're getting a little bit bigger because the areas are getting taller. Right? Okay? Why is this one equal to 1? If the right edge is at x equals 2, well, 2 squared is 4, so the height is 4, right? Doesn't that make sense? Just to kind of, so you can get your bearings a little bit. So out here at 2, the height would be 4, right? There's 4, and the width is 0.25. Well, what's 0.25 times 4? Yeah. So it all makes sense. So it gives me the areas. But what I really want to know is, what's the cumulative area? right? What I really want to know is what's the sum of all these things. So I could define another function. I'm going to call it capital R sub I, or capital R of I, which is going to be the sum of each of the individual areas, which we called A sub I, as I goes from, oh, hang on. Oh, yeah, okay, yes, N goes from, hang on a second, can I screw that up? I think I did.
It'd be as I goes from 1 to 12.
Should be, I think I should do this. Yeah, that's better. Now, I should probably call that like a K. Okay, because look what we're doing. Now we want to know what's the cumulative sum of 1 through, I'm just adding up all the rectangles up through I. So if I add up all the rectangles through 1, well then it's just the same height, the same area as that first rectangle. But when I add up the first 2, then I get the sum of those 2 values, which is that value. Okay, now let's look at this expression then. So R sub I, or R of I, is saying the sum of all the rectangles up through the ith one. Well, then my index variable for the summation has to be something else. I'm going to be adding up, I'm going to be summing up from, let's say, k equals 1 up to I, right? So I got to do A of k. Does that make sense? Because this is like saying if I equals 5, then I want to add up rectangles 1 through 5. See what I'm saying? Okay? And we can see then that we end up with this cumulative area if we do that. And if I go all the way down to 12, I should be able to, there's my answer, right? So the answer that we calculate, if I go all the way up through 12 of those things, I get a total answer of 22.9 is the right area. It's a little bit too big, right? It's a little bit of an overshot, but that's what we get. Now, we could do the very same thing with the left subinterval. Okay? How would we define that one? And where is that? Okay, I'm not going to put so much stuff in this one. Let's just calculate. Is that working? Oh, that didn't look right. Let's just do this. There we go. This is what I want. Okay. I'll come back, we'll talk about this more later. But so let's say we're going to set I to be 1 and B, or A to be 1 and B to be 4, right? If we let the number of rectangles equal 12, I'll show you what you get when we look at our answers. So we said we got for our right subinterval, we got 22.9. If we do the same thing for our left subinterval, where we're counting, the heights are based on the left edges, we would get 19.15. So we should expect our answer somewhere in between. Okay? All right. Enough of that. And here you can see here's all the individual areas. If I add all those up, they represent all 12 of them, I get my 22.9. Okay? And here you can see, here's what the result you get if you add up the individual left areas. And once again, you can see, look at the connection. If I'm looking at the right sum and the left sum, there's the first rectangle, there's the first, there's the second one. What do you see? See the connection? Okay. So that works fine. But now, what if we want to be more general, right? Because we don't necessarily want to pin ourselves down to just 12 rectangles. We want to be able to vary the number of rectangles to be whatever we want it to be. So let's keep it totally general. Let's call it N, right? So then, what would if we're just going to leave it N rectangles, haven't defined how many, the interval we're going to keep that general too. Instead of starting at 1 and ending at 4, we're going to start at A and end at B. if we're gonna use the same approach where we want the width of each rectangle to be the same, so it's simple to add these up, what's gonna be the width of a rectangle? Once again, the region that we're trying to add up the area under the curve from x equals a up to x equals b.
Delta x over the number of intervals.
Well, we're going to define the width, by the way. We define the width of each subinterval as delta x. Right, and that's consistent with this whole idea of delta means like a piece of something, right, a change in something. So the change in x for each rectangle, that's going to be the width, right? The change in x defines the width for each individual rectangle. What's going to happen to the width of the rectangle if we leave the length of the region the same, but the number of rectangles gets bigger? What's that going to do? Right, what's that going to do? If I'm going to go from 1 to 4, let's say, and instead of 12 rectangles, I'm going to use 100. What's that going to do to the width of each rectangle? Shrink it down quite a bit, right? So let's see if we can come up with a way to predict exactly what the width would be. And we don't want to pin ourselves down to 1 and 4 anymore. We're starting at A and we're ending at B. What do you think? What divided by what? What did we do last time? We said it was 3 divided by 12. How come? Because 3 was the width of the interval and 12 was the number of rectangles. If we divide 3 by 12, it gave us the 0.25 being the width of each individual rectangle.
So b minus a.
Okay, so isn't that the width of the interval is b minus a divided by
Number of intervals.
what do we call the number of rectangles? Yeah, there it is. So that's our definition of delta x. It's always just going to be b minus a, the width of the interval, divided by n, the number of rectangles. Okay, good. So that we got that knocked out. That's one thing. Now we got to figure out, using that, how are we going to be able to define, for example, what the right edge of each subinterval is going to be. Okay, so if it's an increasing function, we'll assume it's the same as we just looked at, an increasing function. That's going to give us the heights of the circumscribing rectangles. How can I do that? So we could call that, let's say, x sub I. So if we want to label all of these places, we would say that we're starting off, A we're going to call x sub 0. X sub 1 we'd call the end of the first step. And once again, we're starting at A and we're taking steps of width delta x. So now I've taken 1 step, so I'm at x sub 1. 2 steps, I'm at x sub 2. 3 steps, I'm at x sub 3. I steps, I'm at x sub I. N steps, I'm at x sub n. I'm all the way to the end, right? X sub n is b. Okay, it's all the way across the interval. How would we define then for x sub I? We're going to take this random, we're picking it totally at random. We're going to take the ith subinterval, which is just somewhere in between a and b, but it could represent any of these depending on the value of I. If I is 1, it's that one. If I is n, it's that one, right? But just completely general, how could I say what's going to be the right-hand edge of the ith subinterval? Because I need that x value to calculate its height. Once again, what am I doing here? I'm starting at what value? What's my starting x value? Well, no, but general. A. Okay, it could be anything. We're saying it's A. And if I'm at the right edge of the ith subinterval, how many steps am I taking? I. And how wide is each step? No, what do we?
B minus A.
So just delta x, which we know means b minus a over n. Okay, so then what's x sub I equal to? It's going to be my starting value, which is a, plus, how do I get to the right edge of the ith subinterval?
Add delta x.
Times how many though? Times I. There it is, right? Does that make sense? Okay. What would it be then? So if I is 17, then I'm starting at A, it's A plus 17 times delta x. If A is -4, then it's -4 plus 17 times 17 times delta x, right? And we can always calculate delta x. Okay? What would it be if I want to calculate the left edge? The left edge of the ith subinterval, and remember, this is subinterval number I, right? That's what this is, subinterval rectangle number I. So the right edge is x sub I, the left edge would be x sub I minus 1. So x sub I minus 1 is just a plus how many steps this time to the right? Instead of I, I'm taking I minus 1. Okay? Which one do you think looks like it's going to be more convenient to use when we're calculating areas? The right or the left edge?
Right.
The right edge. And actually by quite a bit. Adding that extra I minus 1 in there really bungles up the math. It just makes it more complicated looking. There's more writing to do, more to keep track of. So we always want to try to use this one. Peering ahead a little bit, how are we going to get the exact area, do you think? We kind of talked about this already. If I want to get the exact area under the curve, what am I going to do to the number of rectangles? It's going to take a limit as it goes to infinity. So does it make any difference, do you think, which one we actually use?
No.
No. Either way, we're going to get a perfect answer, so why not use the easiest way, right? Okay. So then, that's how we define right edge and left edge. And now, we can use those to add up left sums or right sums. But the question is, how do we do that? Because now we want to try to do a corresponding thing here. We want to try to add up the right sum, let's say, being completely general. We've only got 3 minutes, so this is a great place to end. Okay, but you can kind of see where we're going with this. That whole process that we did on Desmos, where we found an algorithm for adding up the areas. We're going to add up the areas this time, but we're adding up the areas as the number of rectangles goes to infinity, right? But we want to be able to come up with some completely general way to do that. And we haven't really specified anything, have we? We're just going to leave the function as f of x, so that's not specific. It could be anything, right? We're not going to specify where the boundaries of the interval are. We're calling those a and b, right? And we're saying the number of rectangles is n. So there's nothing at all specific about this. So the beauty of that is, if we can come up with an algorithm for doing this, it's going to work how often?
Every time.
Every time. All we got to do is apply the specifics of our situation to that template we're going to build, and we'll get the area that way every time, right? And so you can see what's going to come out of this in a really surprising way is a beautiful shortcut that's going to make this thing just so short you can't believe it. It makes this whole process unbelievably easy to do. And that's one of the most gratifying things as a math geek, and you guys are all math geeks, hopefully, and you should be. As a math geek, that's one of the most gratifying things about math is when you can see something like that happen. When you can take something completely abstractly and you can show that in every case we're going to get this beautiful, simple way of doing something that always has to apply. And that's what we're going to see. Is it what? No,
It's integral calculus.
it's going to be, yeah. I'll let the cat out of the bag. Somehow this is going to connect to integral
Put
calculus.
the number that you're going to above and the number you're